Welcome all to the fifth edition of the fifth entry, let's say, of the webinar series. Today we have Professor Harshinie Karunarathna, who is a personal chair in the Faculty of Science and Engineering of Swansea University in UK. She's a specialist in coastal and estuarine hydro-morphodynamics. She has over 20 years postdoctoral experience. Professor Karunarathna has extensively worked on computational modeling of coastal hydrodynamics, morphodynamics, coastal flood risk, and environmental impacts on marine renewable energy, and has published over 150 research articles in journals and conference proceedings. So today, she's going to present a work on climate change impacts on ocean wave energy, and I leave the floor to Harshinie.
Thank you very much, Joseph, for the nice introduction, and good afternoon to all of you. I think I should thank the organizers of this series of seminars actually for inviting me to giving the talk today. Okay, so I'm going to talk about climate change impacts on ocean wave energy, taking a case study from the Indian Ocean. This work came out of a project we did a couple of years ago, which was funded by the Global Challenge Research Fund of UK. The fund was provided through Swansea University, and the project was done in collaboration with the University of Monsoon, Sri Lanka, and in association with Kyoto University, Japan. Actually, Bahare sitting here is part of this project, and also Kasun. Okay, so stating the obvious, we know that there are lots of different renewable energy sources that different countries try to exploit, won't work out, and all that. So, like hydropower or solar and geothermal, or maybe offshore wind. But in that, marine energy, including both wave and tidal, has a special place because of so many issues, so many reasons. For example, if you think about wave energy, abundance is one of the main things that it makes people think and favor that. And also the wide geographic spread. For example, if you take countries surrounding seas, most of the countries may have enough wave energy to harness if they want to. And then obviously, you can do offshore and nearshore harnessing, and we have proven technology. Well, I kind of bluntly say we have proven technology, but if you listen to the talk by Dr. Matt Foley a couple of months ago, you could have, you must have anyway heard that, most of the major wave energy companies went into administration, which is a bit of a drawback to the wave energy in the world. But it's good to see that new technologies are emerging, so we may see a bright future for wave energy soon. Okay, so a couple of years ago, we did a study in Swansea University. We tried to sort of find the global wave resource and categorize the global wave resource. What you see here is a map of wave resource around the globe, which was done based on multivariate clustering. So here we use W classification method based on ECMW ERF5 data, and tried to find out where the resource is and where actually where you have the highest resource or the lowest resource, and so on. And you could see that if you look at it now, green, yellow, orange, and purple, red and purple, mostly for the higher sort of level of higher class energy classes, the availability. And you could see that most of the areas around the Indian Ocean has quite significant wave energy resource. So, and in this plot, you could see this gray line, which indicates the line where the wave energy resource is bigger than 15 kilowatts per meter. It's a kind of standard. We think that, okay, this is quite, abundance energy. And you could see many of the shorelines around the Indian Ocean nations fall into this, exceeds this 15 kilowatt per meter threshold, which shows us the potential in the Indian Ocean. So that is one of the the reasons. That is where we are at the moment. And then going into climate change impacts, of course, it is obvious. We know that climate change is true, it happens, and then the impact on the wave in the ocean is imminent, we know that. And there is a lot of proven studies to explain how much the climate change impacts will impact the ocean energy and so on. But of course, we know that it is not the same. It is not that everywhere the oceans will be much more intense, or wave energy will be higher and so on. But fair proportion of places around the globe will be impacted by the climate change. So with that, the outline of the presentation actually is here. Now, first I'll talk about I'll give you an in-depth analysis of wave resource. And then I'll talk about climate change impacts. In this case, taking a case study approach. I'm not going to do an overall sort of global study or overall Indian Ocean study as such, but just, how these things, taking a case study approach, I'll talk about this particular case. Now, going into an in-depth study of wave energy resource, I'm sort of borrowing some of the work Baharit and Professor Nobumori from Kyoto University did a couple of years ago. So putting you into context of larger scale. In this study, they developed a computational model for the Indian Ocean, wave model for the Indian Ocean. You can see the model boundaries here. And with a spatial resolution of 0.5 degrees. This wave model is forced by global climate model from Japan Meteorological Agency, and then what they did was they simulated waves in the Indian Ocean for two time slices, one covering the historic 1979 to 2003 period, and then the next one, the end of the century or future scenario where the time slice between 2075 and 2099. So following this study, they concluded that, okay, they found out the impact of climate change on the waves in the Indian Ocean. That's what you see here. If you look at the first column, the top figure here is the significant wave height, relative change of significant wave height. And the bottom one is the change of energy period as a result of climate change. So it is clear from this that, the impact of climate change on the wave height is pretty clear, although most of the larger changes were concentrated in certain areas like these, okay? And same is true with the wave period, but, it's more of the wave height that has been impacted. So they dig a little bit deeper. Okay, so annually, on the average sense, there'll be changes, but what happens with the seasons? So they divided an year into 4 quarters, starting from December, January, February, and March, April, May, and so on. And then they were able to recognize the seasonal aspect of this change. And then they went in to see a little bit more in areas closer to the shorelines to see, where actually these impacts will be felt more. So that's what, so the results are given here, which gives you the historic and future of significant wave height and the swell and, energy period, and finally power, showing the areas where the changes changes will be imminent. If you sort of concentrate on this one here, wave power, which is the focus of the talk today, and look at the historic and the future power around the closer to coastlines, you don't see that much of a change. But we need to note that, the resolution of this model is 0.5 degrees. So probably at this scale, we don't see that much of change, but still you can see some changes at various places. So that was the basis of our study. So we know that the things will change, but we don't know how much when you talk about, certain countries or certain regions. So that is where this project came. Now, we took Sri Lanka, a small island nation in the Indian Ocean, as our case study. And there were plenty of reasons for us to choose Sri Lanka. Now, as you see, this is the map of Sri Lanka, and I think all of you know where it is. We are just by the, it is by the side of, towards the east of India, quite close to India. Actually, here you see part of India in the map. So the Sri Lanka just lies by the side. And the country has a very shallow continental shelf. So you can see that from in this figure, that the shelf in lighter colors here is quite very, very shallow. The deepest may be 200 meters. And the shelf, at the and then the deep ocean starts very, very, very rapidly. So it's a very steep shelf, which is kind of very good for wave energy harvesting, because it's easy for installations, easy for maintenance, easy for grid connections, and there are so many positives of having such a shallow continental shelf around. And also, Sri Lanka has a very energetic wave climate all year round, and beyond Sri Lanka there is nothing until the South Pole. So it's open ocean, very large fetch. And the wave climate, at least in the west and the south, is governed by the southern Indian Ocean swell, and of course modulated by tropical monsoons coming. So the southwest monsoon reaching from May to September from the southwest of the country, and the northeast monsoon coming from the opposite side. And they'll have occasional cyclones, but not much. I wouldn't say very rare, but relatively rare. So that is also a good thing, because you don't have sort of extreme conditions, which is again favorable for wave energy generation. So, and then at the moment, if I talk a little bit about the energy situation in the country, most of the energy at the moment is provided by either coal or diesel plants, unfortunately. But hydropower actually contributes about a third of the energy demand in Sri Lanka. So, but the Sri Lankan government is committed to, make the energy mix more or less renewable, in the near future. So the Sustainable Energy Authority of Sri Lanka, who are responsible for exploring possible options and contributing to make strategic decisions about the energy future in the country, considers these four sources as the potential energy sources for future. For example, extending the hydropower schemes and the solar. And also a little bit of biomass is contributing to the energy mix now, but not a lot. But the government think they can extend that, and also wind energy. So you see, wave energy is not currently in the list, and that actually is due to a certain some reasons or some challenges, I would say. Some of these challenges are global, as we know. All of us know the challenges of marine energy generation, but some of them are local. For example, lack of research and technology. So nobody invests or focus on doing research on marine energy, or particularly wave energy. And the other thing is this: the market is very small. Sri Lanka has only 22 million population. So, it's not like a developed country. You're looking at a really, so small, comparatively small market. And that actually links with the other thing where the country largely depends on development from foreign investors, which is linked with the small market. Investors are not interested in small markets, isn't it? So all these things actually contributes to why Sri Lanka is not considering wave energy as a potential contender for future renewable energy mix. And that is actually the motivation of our study. So we thought, okay, so this lack of research, lack of awareness probably may be a contributing factor. So we decided, okay, we can do something here, because Sri Lanka has one of the highest wave energy potential among the countries in the Indian Ocean, as you can see in this map here. And then we thought, okay, we would provide scientific evidence required, at least initiate providing scientific evidence to strategic decisions regarding wave energy mix, and see the potential and understand the potential. So for that, we need an in-depth study. We need to know, details about the source, details about, how the geographic spread, details about the sustainability in the future, and so on. And also we wanted to see the viability of small-scale nearshore developments. Being a developing country and a small market, perhaps very large-scale wave energy developments may not be an option, but there is quite a bit of room to go for smaller scale nearshore development. So that is another reason behind it. And then to look at, implications of climate change and how that will impact the sustainability of wave resources around Sri Lanka. So to give you a bit of understanding of the wave climate around Sri Lanka, what you see here is a wave record, a wave height, and the wave period at a point somewhere in the south coast of Sri Lanka. So you see the red dots are swell and the blue ones are sea waves. So you could see that the wave heights of the sea and swell waves are more or less in the same sort of. They are very similar. But if you look at the wave period, you can clearly see the swell component with the average wave period of about 13 to 14 seconds, and the wind waves are considerably smaller, where the wave period is about 5 seconds. And the waves approach mainly from the south for most of the year. But during a certain period of time, I'll talk about it later in more detail, then the wave starts reaching from the southwest. Actually, that is something to do with the monsoon. So southerly waves coming in, and you can see the seasonality which is associated with the monsoons, and the very strong swell component reaching the shores of at least the west to south coasts of Sri Lanka. Okay, so my computer has become a little temperamental, sorry. Okay, so with that, we started off doing quite high resolution wave modeling for Sri Lanka. And what actually, Bahare actually did all the wave modeling. So what has been done was that we downscaled waves, the results from the Indian Ocean model into the Sri Lankan scale through an interim India wave model, as you can see here. So this large one is the Indian Ocean wave model I talked about earlier, which was used to provide boundary conditions to downscale waves into an India model. And then following that, that was further downscaled into a small Sri Lanka model, as you can see here. And in the Sri Lankan model, which we used to do this analysis, the resolution was 0.05 degrees, so it's about 5.5 kilometers, quite reasonable resolution, high resolution. We used the same simulation period, so the historic covering 1979 to 2003, and then the future, or rather end of century time slot between 2075 and 2099. Okay, so before going into sort of using the simulated wave results to assess the wave climate or the wave wave power around Sri Lanka, we did some model validation as far as we could do, because there were quite a lot of challenges in this validation process as a result of lack of data. Sri Lanka only had one measured wave record for its entire history. So, but still, you know, we had limitations, or we had difficulties in accessing those data and so on. So we did whatever we can. And we then combine that with ERA interim wave data, and then try and validate the model as far as we can. So you could see some comparisons of measured waves with the ERA interim and the modeled wave data. So when we are comparing with ERA interim data, we use the closest grid points we can find. So you could see, you know, the wave heights more or less look quite you know, compatible with each other, and see, so does the average wave conditions as well. You could see they're all quite similar to each other, which gives us you know, reasonable confidence. And in these figures, in the right hand side here, you could see comparisons at with ERA interim data at two locations, P1 and P2. My cursor is doing a crazy thing. I can't sort of move it as the way I want, unfortunately. It's going everywhere that I don't want it to. I don't know why. So anyway, so these validations, as you can see, gave us, you know, they are quite gave us confidence to move forward, because the simulated data matches reasonably well with ERA interim data and also the buoy measurements. Okay, so what you see here is an energy map, average wave power, average over the entire historic simulation period. And then we calculated the wave power based on, you know, standard equations available. You're familiar with the equations that you see here. So you could see the northwestern part up to the southeastern part of Sri Lanka is, you know, contains quite significantly high wave energy resource. Whereas this part here, north and the east, still have a reasonable amount of energy, but not as much as the areas down here. And even on the continental shelf, the amount of available energy exceeded 15 kilowatt per meter, which is quite nice. So that, you know, that makes most of the western, southwestern, and the southern part of Sri Lanka suitable for wave energy harnessing. And then we went to, we dig a little bit deeper to see how this varies around the year, because we know monsoons have a great impact on the wave climate in Sri Lanka. So what you see here is the distribution of wave energy, available wave power in each month. So you can see that you have a quiet start to the year on average. So in January, February, March, and April, the energy resource is around less than 15. It's just made the mark of 15 kilowatts per meter. But then you have a very hyperactivity region, time between May to September, where the monsoon comes, and which increases the available energy resource quite significantly. And then it tails off towards the post-monsoon season. I mean, here it is southwest monsoon, so it's the post-monsoon season here where the things can go quieter. So, so with that, what we did was we went in to do much more sort of detailed analysis to look at the offshore and the nearshore resource. Actually, basically, this was done to inform a Sustainable Energy Authority about, you know, the local aspects, and also the geographic spread and also the nearshore aspects of energy harvesting. So we considered 9 points along the west and the south coast of Sri Lanka, where you find most energy is concentrated. And then we considered corresponding points near shore, quite closest grid point to the shoreline. And we did a comparison of available wave energy. So this box whisker plot gives you a wave power, both near shore and offshore at all 9 points. Now it's the standard, box whisker plot where the central line here gives you the mean, the median, and then the boxes here gives you 75 and 25 percentiles or quantiles, and then the whiskers give you the range. So you could see the difference. So the orange one is offshore and the gray one is near shore. So you can see a clear difference between the near shore and the offshore resource. However, still, the near shore resource is significant. It exceeds 15 kilowatt per meter mark, which makes it still suitable for energy harvesting. And one good thing when you look at this is, the spread is quite narrow for near shore region, whereas energy spread is higher for offshore regions. So near shore, the variability can be smaller, which is again something good for energy harvesting. And then all this is summarized in this colorful figure here, which tells you the variability as well as the available power. So the circle, the size of the circle tells you the amount of power available, whereas the color gives you the variability. Both are equally important when it comes to the stability of the resource over time. So you could see in the west and part of the southwest, the available power is quite high, but at the same time, the variability is quite high. So, but when you go further down to the southwest and then to the south and the southeast, you have quite significant amount of wave power available, but the variability is getting smaller and smaller, which is quite nice. But in the nearshore resource, it's quite consistent, other than only this place here, where the energy is less than the offshore, obviously, but it is much less variable, which is a very positive thing when it comes to wave energy harnessing. Okay, then going into the second part about climate change. What you see in these two maps is the historic and future, historic in the left and the future in the right, average wave power around Sri Lanka. Now, at a glance, you can see the difference. There is a significant difference in this part of the country, if you think about the wave power in history, in the current situation and in future. Although the change, you can't see that much of change in the north and the west. Surprisingly, well, I wouldn't want to say surprisingly, but still you could see that the wave power reduces in future. So we would expect, okay, this, the extreme conditions become extreme, and the wave conditions will be, much more intense in the future. So you would expect wave power increasing in the future, but it's not like that. At least for this situation, it's not like that, where you could see a reduction of power in future. So to see actually what is contributing to this change in reduction in future, we looked at the significant wave height and the energy period separately. Now, if I go to talk about the energy period first, you could see there isn't that much of a change. What you see here is the difference between future and historic. So you see from the contours, you can see the change is very, very small. So the energy period is more or less stable in future by the end of the century. But if you look at the wave heights, that's where the change is. And also the change you could see is much more prominent in the west and the south of the country, whereas it is less so in the east and the north of the country. So we know that it is the wave height actually contributing to the change in the wave power in future. So a little bit more details about that now. Okay, we now know, okay, the wave power is less in future and it is wave height which contributes to this change, but how is the temporal variation of that? So to do that, we looked at the average wave power in each month. So you could see the changes again, this is the change difference between future and historic monthly average wave power. So the first 4 months of the year, you don't see that much of a change, but then during the monsoon season, May to September, you see most of the changes, and then it is sort of quietening down, or the changes are much less towards the end of the year. So, and then this gives us, tells us something, isn't it? So because most of the changes occurred during the monsoon time, now we know that most of these changes should be or may be related to the monsoons, the changes to monsoons as a result of the climate change. And we wanted to look at it in more detail geographically, because now we know that most of the country from northwest to southeast are suitable for energy harnessing. So we need to know a little bit more in detail geographically how these variabilities impact different parts of the country. What we did was we considered 10 different points along the coastline as we did before, but now these are different points. So, and then we looked at how this geographic spread or how this variability impact the geographic spread of the country. So here's another box Whisker plot telling you historic and future wave power at these 10 locations we selected. Again, the present representation of the box and the whiskers are the same, where the median and median 25 and 75% percentiles are given in the box, and the range is in whiskers. And the gray represents historic or present situation, and the orange the future. So you see the various variations. Now, if you look at these 3 points and even these 4 points, M1 to M4, which is more in the northwest and the upper part of the west, there isn't that much of a difference between the future and the historic situations. It's very, very similar. But from point M5 up to point M8, which is in the lower part of the west and the southwest of the country, you can clearly see the difference between the present and the future available power. And then again, as you go down towards the east, southeast of the country, there isn't that much of a difference. So one thing you can notice here is that, okay, there is a small reduction in wave power, but if you look at the spread, there isn't that much of a difference. A slight difference, but not much. So it remains the same, but overall, the available resource will be less. And then we looked at if there are any changes to the wave approach direction or the direction of the monsoons and so on, but we can't see much of a change. I mean, what you see here is the wave power roses for historic and future situations. You could see that at a glance that the direction hasn't changed much, although the power classes may change slightly. So we know that okay, the changes in the future or the impact of climate change is visible, but it is mainly due to change in wave height, not the period. And the changes are mostly linked with the monsoons. So mainly it is during the monsoon season or changes to the monsoon as a result of climate change will change the wave climate. And there is no changes to the main or primary direction of wave approach or where the most energy is concentrated. So both wave period and the direction are much more stable, whereas monsoons will change the wave height in the wave climate. Now, This scatter plot, I don't want to look at, I won't expect you to look at or read this in numbers or anything, but just I used it to highlight, one or two things, for example. Now, I'm just sort of focusing on the 4 points in the west and the southwest here, where most of the wave energy wave power is available. And if you follow my, red broken lines, you could see the range of wave periods where most of the energy is concentrated in these 5 points. You see the wave periods are between 8 seconds and 12 seconds. So they're more or less, quite nice swell reaching from the Atlantic, which is quite nice because we know, if we can harness swell waves, they are much more stable and they are more, the variability is less. So this tells us Sri Lanka has a very, very favorable situation for wave energy harvesting, both near shore and offshore. And so we see this change of wave power, available wave power or the wave resource over these 2 time slices, historic and end of century, but it is, nearly 100 years apart. So how about much more sort of smaller scale changes? Is the wave resource stable over a shorter period of time? So to find that, what we did was we looked at the average annual wave power in each simulation year in historic time slice and the future time slice. So in the left-hand side, you see the historic figures, and in the right-hand side, the future figures. And the blue line gives you the historic, the historic value. Sorry, I think I said something wrong. So the left-hand side give you the points from M1 to M5, whereas the right-hand side from M6 to M10. And the blue lines give you the historic wave power, whereas the red ones are the future wave power. And the broken line is just the difference in the scale here in the right-hand side. So you see, if you look at a 25-year period, obviously you see some, annual changes. That should be quite obvious, isn't it? Other than that, you cannot see a upward trend or downward trend, which tells us over a shorter period of time, within let's say a few decades, the power is quite stable. So all these changes will be quite longer term. So that is kind of reassuring for us, because if you look at wave energy developments, we are talking about, lifespan of 25 to 50 years maybe. And then if the resource is stable over a few decades, it's give you much more reassurance for, going for these kind of developments. So although we expect very long-term changes over a scale of a century, towards the end of the century. But if you look at decadal scale change, then the changes are not significant, or at least we don't see upward or downward trend of available power. Okay, so the monsoon effect. To look at it a little bit more in detail, these 2 figures in the left-hand side, you see the difference between future and historic annual mean wave height, significant wave height during the monsoon and outside the monsoon here. And you could see the change is quite significant during the monsoons here, whereas outside the monsoon it is less so. So we know where the changes are coming and why the change occurred. Okay, so with that, finally coming into my conclusions, and the Sri Lankan wave climate is characterized by the long distance southern Indian Ocean swell, and also locally generated. I mean, when I say local, it is not local as such, but it is mostly some local generated waves plus this, monsoon generated waves. And then west to southeast coast of Sri Lanka has, wave power varying from 9 to 21 kilowatts per meter, which has a significant geographic spread going from the northwest to southeast. More than 50% of the time in a year, near-shore wave power potential from west to the southeast exceeds 10 kilowatt per meter, and which is quite encouraging. And wave power potential in the southwest to southeast coast of Sri Lanka is significantly influenced by the southwest monsoon, as you saw, and the wave resource is stable over these 25-year periods, both historic and also in the future. And future, well, when I say future, I mean, you have to put it in the context, because the results we have, the wave simulations we have are at the end of the century. So here we are talking about 10% lesser wave power available towards the end of the century as a result of climate change, primarily because the changes to monsoon seasons associated with the global climate change. Okay, so that's about it. And then, so one more thing is that, nearshore developments are also a possibility in the context of Sri Lanka, which is more realistic, I think, than larger scale offshore developments. So just for your information, all these results were published in 3 journal articles in the journals Energies and the Engineer Journal in Sri Lanka. So all of them are open access, so you should be able to approach them, access them if you want to. So finally, I would want to acknowledge everybody who contributed to this study, to the funder, GCRF through Swansea University, and also to especially to Dr. Bahare Kamransad, who did all the wave modeling and provided data for us to do this study. And our MSc student, Mr. Praveen Madhuwanta, who did all the hard work doing the analysis for this, and Dr. Kasundi Silva and Mr. Harshinie Surya, who hosted the project at the University of Moratuwa in Sri Lanka. Thank you.